Okay, let's begin. This is the fourth lecture in the turbomachinery series, and we're going to continue with the problem we were working on in the last lecture. Going back to the document cam, there's one thing that I neglected to mention as one of the givens here, and that is you're going to be, in this case, you're given that alpha 1 is 30 degrees. Okay, so that means this angle is 30 degrees. Now, because of that, and because of this symmetry, you should be able to show, or just from geometry, that if this is 30 degrees, this angle is 30 degrees, then actually beta 2 is 30 degrees just from geometry. Okay, so if you're given this, and you're given these velocities that result in a symmetric velocity triangles, you should be able to work that out. So on an exam, if you're just given alpha 1, and now you're down trying to calculate W theta 2, and you need A beta 2, you actually know beta 2 just by looking at, and this is what I meant by getting comfortable with working with these triangles. Okay, so continuing now, I know beta 2, and I know W2, so this is nothing more than 140 meters per second times the sine of 30 degrees, and so I get W theta 2 is 70 meters per second. Since I know alpha 1 now, and I know C1, I can get CZ1, right, which is nothing more than the square root of 140 meters per second minus 70 meters per second squared, square root. Actually, you're going to say, well, where did you get this 70 from? You haven't calculated C theta 1 yet, and you're right. So before you get to here, you now look at C theta 1 as C1 cosine alpha 1, which again is 140 meters per second times sine of 30. And so C theta 1 is 70 meters per second, just like W theta 2, it's all symmetric. So this is what goes in here. CZ1 is then 121 meters per second, which means you know what CZ2 is because we said we're assuming those are equal. So I know the tangential relative velocity at 2, I know the tangential velocity at 1, I know CZ. What I really need to get to is C theta 2. There's several ways you can do that. One way is just to continue on getting the rest of the tangential components. W theta 1 is going to be W1 squared minus CZ1 squared, and I get this to be 207 meters per second. This is helpful because eventually I'm going to need to know what U, the wheel speed, is. Okay? And I can say now that W theta 1 plus C theta 1 is equal to U. So then this is 207 meters per second plus 70 meters per second is equal to 277 meters per second, and now I know the wheel speed U. And real quickly I can find C theta 2 now, which is going to be U minus the relative tangential velocity at 2, 277 minus 70 meters per second. So C theta 2 is 207 meters per second. hopefully that's bigger than c theta 1, which we found to be 70 meters per second. So yes, work is being put into the flow. So now that we have that delta c theta, it's now just a simple matter of calculating the total pressure ratio using our equation we defined before, U delta C theta over CP T1. And now we know everything that goes in this side. Of course, this was gamma over gamma minus 1. When you plug this in, you get 1 plus 0.85, 277 times 207 minus 70 over 1006, if you recall our value for CP in SI units, and 300K we were given. And this is 1.4 over 1.4 minus 1. And when you plug and chug, you get 1.43. So that's a pretty healthy pressure ratio for the eye. That's putting a lot of work in for one stage. Okay? So that's how you would work through the calculation here. And again, the difference here is that we were making use a lot of geometry. In this case, things are symmetric. Given a certain angle, I was able to go through and quickly calculate from basic trigonometry some of the values that we're interested in. Now, I'd like to talk now about expressing the work equation, or the in terms of flow angles, just in a different way. So let's consider our at the downstream side of the rotor. So assume that we have, here's our rotor, and this is 2, and this is 1. That at station 2, at some radius, we have some axial velocity, CZ, obviously CZ2. We have some absolute velocity vector C2. We have some relative velocity W2. We've done that in red. Beta 2, and this is alpha 2. And of course, this is the tangential relative velocity, W theta 2, and this is the tangential absolute velocity, C theta 2, and they are joined together by the wheel speed U. Again, just so you remember, U is equal to omega times whatever radius we're talking about here. Okay, so just from this geometry, we can say that C theta 2 is equal to U minus W theta 2. That seems to be obvious. We can also say that tangent of beta 2 is equal to W theta 2 over CZ. Let's call it CZ, even though it's CZ2, right? And so substituting in for W theta 2, we get C theta 2 is U minus CZ tangent beta 2. We also know that tangent alpha 1 is equal to c theta 1 over c theta 2, or excuse me, cz, right? And so using that fact, we can say that c theta 1 is equal to cz tangent alpha 1. And now substituting into our work equation, delta c theta over u, normalized to u, which is the same, remember, delta work put in over u squared. Go back and look at that equation that we had and substitute, you'd find that you can make this equivalence. And this is nothing more than 1 minus cz over u tangent alpha 1 plus tangent beta 2. By the way, this is at station 2. This is obviously at station 1, and this is just simply CZ, assuming CZ is the same between 2 and 1. This is C1, this is alpha 1, this is C theta 1. The performance of a single stage axial using velocity triangles, as we said, we can use this for C theta 2. We can use this for C theta 1, and explicitly derive this expression here, which you should be able to show given our relationship for enthalpy rise versus delta C theta that we derived earlier. So what happens when we consider a multi-stage axial flow compressor and we slightly perturb the incoming mass flow? Like sort of like when it starts, right? There's a design mass flow that it's meant to pump, okay? The flow path and all of those stages. So what happens when we have identical stage characteristics? So if we consider a multi-stage compressor, axial compressor, with identical characteristics, identical stage characteristics, really. That means that each stage has roughly the same type of air angles, right, going from one stage to the other. So that what that means is that CZ over U, the normalized axial velocity normalized to the wheel speed, is the same for all stages. Right? So that's what I mean by identical characteristics. So this is some design value. Right? The air angles and all this are designed such that that ratio is the same for all the stages. So let's think about this condition. If U is constant and the inlet mass flow to the compressor is slightly reduced, then the work, right, the normalized work, will increase at the first stage. Okay? So again, slightly reducing mass flow for the same wheel speed. So this thing is spinning at X RPM. Okay, at a given radius, U will stay constant. If we slightly reduce the inflow, that means that the normalized or the specific work done is going to go up, right? Something over m dot is going to go up at the first stage. At the entrance to the second stage, so at entrance to the second stage, CZ over U will go down. Why? Because, first of all, m dot was down, right? We said before, and the density will go up. So that means that for a greater decrease in the CZ over U from the design point in the second stage causes even more work to be done and density to go higher. Okay? So again, let's back up. I've got this multi-stage axial flow compressor. So I've got all these, I don't know, X number of stages. I'm just going to draw a few in here. And there's some design CZ over U. Okay? Some axial flow divided by the wheel speed at some design point. And what we're saying is what if this m dot coming in here is dropped just slightly? Okay? Well, what's going to happen at the first stage is that there's going to be a slight increase in the work done. Okay? And the consequence of that is what goes into the next stage, this is stage 1, this is stage 2, is that CZ will further decrease. If CZ further decreases because because density is going up and mass flow is going up, that means that there's more work that's going to be done by stage 2. Okay? So you get a greater decrease in CZ over U from the design point at stage 2 of the multi-stage compressor. Okay? This creates, or causes, I should say, even more work to be done at second stage, or by the second stage. Right? So that means the same rho will increase, and this goes into the third stage, and so on. So this builds, if I had 10 stages of compressor, okay, just a slight decrease in mass flow in the inlet is going to cause more work to be done by each successive stage, right? What is the implication of this? The implication of this is that I'm going to end up having a even further adverse pressure gradient, okay? And I'll probably most likely separate this ultimately leads to separation of flows in the rear stages. Okay? Now what this means aerodynamically is that I've got some beta design. And in the rear stages at starting, I'm going to have a much higher beta 1 than design. Okay, so this would be maybe at starting, and this is design. Okay, what that translates into is that if you call our definition for incidence angle, right, I'm going to have a larger incidence angle. So think about this as having a larger angle of attack, and indeed I could be in that region where I could actually stall. Okay, the opposite for a moderate increase in inlet mass flow. Okay, you would just get a negative incidence angle or a negative angle of attack leading to a stall in that condition. In fact, this could lead to a significant problem in that you're literally closing down the flow area more than the actual geometric area, and the back of the axial compressor will start acting as a throttle, okay, as you're trying to start up this axial compressor. Okay, so this is what's known as the starting problem, okay, for an axial compressor. And essentially what you have is, in the first stages, you have, your design, and then you have something that would look like that, and in the rear stages, you would have the beta 1 and the dashed lines are what you have when you have a slightly decrease in mass flow, and the solid line would be the starting condition. So in this case, we'd have stationary, starting, and the dashed line would be design. So the density would be low and remain low during starting. DZ is low, but large enough in the rear stages to choke flow. And this leads to decreased loading. So, low density operation tends to overload the leading stages and this prevents proper compression. Recording. So how do you take care of this problem? Well, what was you could increase the M dot at the front. So solutions to this problem, which when they first started building axial flow compressors, we're talking about the early 50s now, early 1950s. You can increase M dot at front. You can have or introduce, and this is what was done to fully solve the problem, is introduce the concept of variable stators. Okay, and we showed a picture of what these things were in an earlier lecture. So now, instead of having this static airfoil design through the compressor, if I have the ability to change the air angle, which effectively means what I'm doing is I'm going to change beta, okay, by changing the stator angles. So I'm changing the relative angles going into the rotor. I can overcome this starting problem. And then as this spool speeds up and as I pump more and I get more MDOT, I can control that. That thing. The other thing you can do is you can have different, you could basically change U by adding a spool. Okay? Recall, this is on this one axial compressor, right? It's all on, we were assuming it's all spinning at 1 omega. Okay? If the front stages spun at a different omega than the rear stages, that would also solve the problem because it would also change the air angles. So I could break this up into two spools, where now this is omega 2 and this is omega 1, and I can have the rear stages spin at a different RPM. Think about what Rolls-Royce does with having 3 spools, right? So they kind of handle some of this problem by having an additional spool. Indeed, if you were able to have each stage independently controlled with its RPM, that would probably be the best because you'd be able to just dial it in and you'd have a more efficient compressor. Of course, the problem with that is that now I've got multiple shafts. Just not practical to have probably more than three spools. Okay. So continuing to talk about the compressor more as a system, a multi-stage system, what are some of the characteristics of multi-stage compressors? Looking at it from a design mapping. Characteristics of multi-stage compressors. Okay, again, I'm referring to axial flow compressors. So you can do the usual Buckingham Pi dimensional analysis, and if you look at total pressure and efficiency of the compressor, they're going to be functions of the mass flow, the inlet total pressure, the inlet total temperature, the rotational velocity, gamma, gas constant R, the viscosity, and the diameter. Okay? And indeed, the pressure ratio, PT2 over PT1, and the efficiency, you could then group into parameters like this, m dot r, square root of r, TT1 over PT1 times d, or over d, and then omega d over square root of r, TT1. Since D and R are fixed for air for a given compressor, okay? So since D and R are fixed for a given compressor, we can write PT2 over PT1. These are functions of m dot square root TT1 over PT1 n over square root of T1, where n here is the shaft speed. Okay, and so what's done now, these are called the corrected parameters. So this is corrected mass flow and corrected speed. So if we define theta as TT1 over the standard temperature, and delta is PT1 over PT1 standard, right? So in SI units, this would be 288 Kelvin, and this is, I think, 101.3 kilopascals. Then we can say that the total pressure ratio and the efficiency are functions of m dot square root of theta over delta and n over square root of theta. So we can express for every multi-stage compressor or even a single-stage compressor, we can look at the pressure ratio, total pressure ratio and the efficiency as functions of the corrected mass flow and the corrected speed. Okay, and this is very useful when we want to compare one compressor to another, especially in terms of its efficiency. So if you build a 10-stage axial compressor and I build a 5-stage axial compressor, how are we going to compare the relative goodness of each compressor? Because they're going to have different pressure ratios. Okay, so the one way you can compare them is to look at them with these corrected flow parameters. Okay, so what's built for both a stage and for a multi-stage compressor is what's called a compressor map. Okay, where on the x-axis we're going to plot things versus the corrected flow, and we're going to plot that versus the total pressure rise. Okay, so what you have here are a family of curves that look like something like this. Where these are lines of constant speed. So in this direction, these are lines of constant corrected speed. Right? This might be, 0.7, this might be 0.85, this would be 100%, and so on. Okay? Superimposed on here would be contours of constant efficiency. And because of the way they kind of look in this plot, a lot of people consider called these efficiency islands. Okay, so these things are constant adiabatic efficiency, and these inner ones here are higher. So this might be, 90%, 80%, and so on. So the ones in the outer bands are lower efficiency, and as you spiral, as you go in, you get close. So, you have, for each compressor, you can generate, if you built a 10-stage axial flow compressor or a single-stage axial flow compressor, you can build this map, and it's actually done, right? And you create these family curves, and then this is where you would end up picking your design point. Okay, I want to operate, here as my, for cruise maybe, and then you can put yourself an off design of where you would be for takeoff or climb, for all those other cases. Okay, so how would you generate a map like this? Well, there's a couple other features about this map that need to be, and it goes to how you would generate this. So if you actually built a multi-stage axial compressor, the way that you map this out is you bring it down to a test cell, you hook it up to an electric motor where you can control the power input. So you're going to dial in the RPM, you're dialing in the shaft work, okay? And then at the exit of the compressor, you'll have some inlet that'll start pumping air through it. The exit of the compressor, so maybe I can, our typical generic picture of, in this case, a multi-stage axial compressor, right? You'd hook it up to some bell mouth here. So if this is stationary in a laboratory, it would just start pumping, and this is all on a shaft hooked up to a motor. Some electric motor giving it some rotational velocity. And then the exhaust here would be hooked up to a throttle. And so what you would do is you would fix an RPM at a given flow rate. So you might start, say, somewhere here, and you would get a point. And you would slowly close the throttle, and you would keep the RPM the same. And so you would move upwards on this curve. You'd increase the pressure ratio as you close the throttle down. You'd increase it again. Keep closing the throttle, until eventually what happens? You get to a point where it completely stalls, okay? And it's before you completely close the throttle. But you get a point here where you've basically, for that particular constant RPM, have stalled the compressor. So you marked it. This is a very important point, okay? It's sort of like if you take an axial fan that you have in your computer, right, and you put your hand behind it. At some point, you'll stall the flow through that fan, and that at that point is the one you mark down. Now, as you keep throttling down or throttling the flow, okay, you're getting a pressure rise, okay? So you're loading up the airfoils more and more, and so you get more and more pressure rise. So that's a good thing, obviously, but you do too much and it stalls. You do that at a variety of different speeds. So then you go to a next speed and you keep repeating this process, and you generate these family of curves, and you identify these points of stall, okay? The locus of points that connects these points here, that's what we call the stall line. Okay? Now, when you operate a jet engine with an axial flow compressor here, and you just push the throttle forward, you're going to move along an operating line that's somewhere here or somewhere like this, right? Where at some point you're going to go through your design point. Okay. Now, it's the relative distance between your operating line and this stall line is how we end up defining stall margin. Okay. So I think what I'm going to do is I'm going to stop there and pick up on the next lecture. So this should have been the fourth lecture. We'll continue with lecture 5 on turbo machinery coming next.